So it's important as teachers that we have effective communication in math, and that requires teachers and students to share an understanding of definitions and of logical structure. But in the classroom, we often mix up formal definitions with more intuitive concept images, and that includes both teachers and students. When this happens, semantic contamination can occur, which means everyday meanings interferes with mathematical precision. That is, right, the way that we sort of interact with terms in our real life outside of math can have an impact on what we mean when we're talking mathematically. And so this comes up a lot because students often rely on their intuitive images, which can lead to reasoning errors or hidden assumptions that students don't even know that they have. Understanding how these assumptions can arise and how they can impact students' understanding is key for teachers. Let's think about an example. What do you imagine your students would draw if you asked them to draw a rectangle? I know for me, I would probably draw something like this. I think most students would draw something like that, or maybe something along these lines, right? Do you think that they would draw a square? Or do you think that they would draw a non-square rectangle? I think most students, when they picture a rectangle, are not picturing a square. And this makes sense because we have a specific term, square, to describe a quadrilateral that has 4 congruent sides and 4 congruent angles. So they may have the implicit assumption that when we talk about a rectangle, a quadrilateral with 4 congruent angles, that we mean one that does not also have 4 congruent sides, because if we had meant to talk about that, we would have called it a square. But by most textbooks and by most definitions, it's not the case. A rectangle can be a square. And so this should be addressed explicitly for students who might not realize that their assumption is incorrect. So the teaching implication here is that teachers should probe for these assumptions rather than just checking for surface level correctness. Let's look at another example, how students understand the meaning of a function. So formally, a function is just a set of ordered pairs of the form little x, little y, where little x is an element of some domain set, which we often call big X, and little y is an element of some codomain set, which we often call y. And it has the property that each x is associated with a unique y. In particular, it has the 2 properties of univalence, which means it means no x is associated with more than one y. Right? In other words, you couldn't have like 2, 5 and 2, 6 as ordered pairs in this function because no x is associated with more than one y. And it also has to have the property of totality, which means every x in the domain corresponds to a y. Corresponds to a y. In other words, every element of the domain has to actually be an input that has an output. And it should have exactly one output, right? It can't be associated to more than one y. That's the first property. But right, this sort of abstract definition of a function is not usually how students picture functions, right? If you ask a student to picture what a function is, most likely they're going to be thinking of some kind of a smooth or continuous curve. And again, this makes sense for students because that's often how we're sort of introducing the idea of a function, is as sort of an input and output, but we often kind of, take an equation and graph it to help students get a sense of what a function can look like. The problem with that is that their mental image is excluding any kind of discontinuous or piecewise defined functions, and that can cause misunderstandings when you get to a lot of different theorems, but in particular when you get to some calculus theorems like the intermediate value theorem. So the intermediate value theorem states that if f is a function whose domain is the closed interval from a to b and whose codomain is r, and if f is a continuous function such that f of a is less than f of b with some real number L in between them, or the other way around, f of a is greater than f of b, where L is some real number in between them, then there must exist a C. There exists a C in the in the open interval between a and b, so you could write C is in the open interval from a to b, such that f of c is equal to L. All right, now, the picture of this that we often draw to give students a sense of what this means is that if you have a nice continuous curve on some interval of real numbers where, let's say, f of a is up here and f of b is down here, and it's a continuous function, so, right, there's no breaks in between, then for any L that you choose in between, for any real number L that's in between a and b, you will be able to find some corresponding value c, strictly in between a and b, such that f of c is equal to L. In other words, if you pick any y value in between f of a and f of b, you can find an x value in between a and b, such that that x value has an output of L. And more often we talk about a corollary to the intermediate value theorem, which helps us to find zeros on an interval. It says if f is a function from the closed interval a to b to r, and it's continuous, and if f of a is negative while f of b is positive, or the other way around, f of a is positive and f of b is negative, then we can conclude that our function f must have a 0 between a and b. In other words, there exists a c in the open interval from a to b such that f of c is equal to 0. Okay, and so a picture of this could be, for instance, we have this closed interval from a to b. We have f of a is negative and f of b is positive, maybe somewhere up here. That just means that your continuous function on that interval from a to b must have crossed the x-axis somewhere, right? You must have a 0 somewhere on that interval, and we can sort of see that happening here. So we're just sort of taking this special case where f of a and f of b have opposite signs, and the L that we're looking for is 0. And so there has to be some c in the interval from a to b such that f of c is equal to 0. Now, we try to give students this sort of intuitive picture by looking at a graph, and that makes sense because we want students to understand what the theorem is saying, and they can kind of get bogged down in some of the notation. But on the other hand, when we sort of give students information about this theorem in sort of a picture way, it might sort of, students might get confused, and they might not realize what assumptions we have within this theorem that would cause this theorem to fail if we dropped them. In other words, they might not realize some of their implicit assumptions here, which are important in order to make this theorem true. Oops, for instance, we saw an example of the warm-up where a student may not have implicitly assumed that when we talk about functions, we could be talking about any function. So the student may have implicitly assumed that when we talk about functions, we mean continuous functions only. Or maybe the student assumed that we're only talking about polynomial functions because those are the most often examples that we give our students. Let's look at another example and see what kind of hidden assumptions that a student could have. So let's say a student writes the following solution on an exam. The question states that for a continuous function f, where f of 2 is equal to 7 and f of 3 is equal to 2, what can you determine about the zeros of this function? And the student answers that by the intermediate value theorem, this function does not have a 0 on the interval from 2 to 3 because both f of 2 and f of 3 are positive, and so 0 is not in between f of 2 and f of 3. All right, let's think about what the student is assuming here. First of all, this student is assuming that we're talking about a continuous interval here. Right? We're assuming that this function f of x is continuous on the interval between 2 and 7. Which we don't necessarily know. It says it's continuous, but it doesn't even necessarily say where it's defined. Maybe it's not even defined on the full interval between 2 and 7. Between 2 and 3. Our x values here are 2 and 3. Additionally, it seems that the student might have taken the intermediate value theorem to state that for a continuous function f on a closed interval, that f has a 0 on the interval if and only if f of a and f of b have opposite signs. They might have taken that conditional statement and interpret it as an if and only if statement. But only one direction of this statement is true, and in this case, the converse of that, right? If f of a and f of b have opposite signs, then f must have a 0 on that interval. That doesn't mean that if f of a and f of b don't have opposite signs, and it doesn't have a 0 on that interval. We can come up pretty quickly with an example of a function that does have a 0 on this interval. It just has to drop pretty steeply hit the x-axis or cross the x-axis, and then come back up again, right? So it's important that students kind of understand, where their own misunderstandings lie or where their own assumptions are that might not be correct. The conditions that are important, for the assumption of the intermediate value theorem, all of them matter, right? We say a lot of things, when we state the intermediate value theorem, but all of those assumptions are important. That includes the fact that f has to be defined on the entire closed interval from a to b. F actually has to be continuous on that entire interval. The conclusion of the statement says that there is a C between A and B, and it's strict inequalities there. So the inequalities for C are strict inequalities. That is, A is less than C is less than B, not A less than or equal to C, less than or equal to B. It needs to be a strict inequality. And then also the interval must be closed, not open. The interval, this interval for the domain, must be closed, not open. And each one of these is essential. If we were to remove even one of these conditions, the theorem itself would fail. So let's talk about why that is. So if we think about the continuity condition, we've already seen how that could fail, right? As part of the warm-up problems we saw, a function could have a jump or a hole, and the intermediate value theorem would then fail. Let's say we have f of a, f of b, and here's f of a up here, here's f of b down here. If you chose an L value right in the middle, and then you had some kind of a jump, then there is no C such that f of C is equal to L, right? We can see that there is no point on the curve that has a y value of L anywhere, never mind on the interval from A to B, right? So it may skip some L values if it's not continuous, because you could have a jump. The second condition, the condition that your function's actually defined on the entire interval, if it's violated, the function might be undefined inside that interval. And so we could have, for instance, no continuous path between f of a and f of b. So let's say, for example, you have the function f of x equals 1 over x. And we look at, say, the interval from -1 to +1. This function looks like this. It's negative at -1, and the output is positive at +1, but it's not defined at 0. And indeed, there is not going to be any 0 on this interval, right? There's not going to be any x value that gives you an output of 0, because this function is never equal to 0, and that's because it's not defined on the entire interval. So we could have no continuous path. The fact that we require a closed interval, so the fact that we want the interval from A to B to be a closed interval is important, because if it's not actually defined at the endpoints, then you wouldn't necessarily, you're not necessarily going to be able to choose an L in between them when it's not defined at the endpoints. And for a strict inequality, you could end up having sort of a trivial solution here. Right, if you allowed for f of a to be equal to 0 or f of b to be equal to 0, then you already have a trivial solution. So all of those assumptions are going to be important for the intermediate value theorem to actually hold as a theorem. So the standard proof of the intermediate value theorem, which uses a nested interval property, uses continuity to ensure that as a sequence A sub n of left endpoints and a sequence B sub n of right endpoints both approach C, and as f of A sub n approaches f of c, and f of b sub n approaches f of c. So without continuity, the limit of that f a sub n and f b sub n might not agree, and f c may not equal the expected value. So the limit of the sequence f of a sub n and the sequence f b sub n might not agree. You could have a jump, as we were talking about. So f of c may not equal the expected L, or the chosen L. Okay, so what does this come down to for us as teachers? If we're trying to reveal students' implicit assumptions, we can help students by doing the following things. First of all, we want to make sure that when they give us any kind of an answer, even if it has some inaccuracy due to some underlying assumptions, we want to validate what's true in their reasoning. What is true and what's correct in their reasoning. We also want to make sure that we reveal any hidden assumptions. If they're assuming the function's continuous, and it might not be. And we can do that by sort of posing them some probing questions that might allow them to think about other types of functions. And then finally, by extending their reasoning, by exploring counterexamples. So if you see that they have some sort of assumption, or you're assuming that they might have some kind of assumption based on their answer, you can kind of pose some counterexamples for them to explore and help them to see on their own why their reasoning might not be correct.